ib3 students, standard level and higher level. Okay, you asked me about engineering physics. Yes, of course, so we can do something with engineering physics. I can present option engineering physics. What is important? Important is that you not find this option in your COCOS because it's not in printed version, but this is additional resource you can find on Cambridge web page. So all you have to do to find this is to go to Cambridge resources. You can write in Google Cambridge resources COCOS book, and then option we are interested in is engineering physics option B. In this window you have to click resources, and here you have download button. You can download it. It's for free for people who have a book. You have a book, so you can download it and open. Okay, I've downloaded. I have this option. Here engineering physics is option B, so I'm going to focus today on a problem called torque. Some of you know this problem. I know that there is one extended essay in this school year about torque. One student asked me about this option, so probably he knows, he's an expert about in the case of this option. So let's do this option. Ready? Okay, so I hope it will be also interesting to you, especially for students who want to study physics in university. Okay, so let's look. First of all, we have to review term angular speed. Angular speed is angle covered in unit time, compared with typical linear speed, which is distance traveled in time, is related with movement in the circle. Let's imagine that you have a circle and 2 points, A here and B here. And let's imagine that object travels in time t along this arc. Okay, so object's linear speed will be given by the length of the arc, d, distance traveled, in time. In the case of angular speed, it will be this angle covered by the object. Linear speed is expressed in meters per second, and angular speed is expressed in radians per second. Of course, there is a link. Let's imagine that object travels 1/4 revolution, so in time, which is equal to 1 period. What is the angular speed? Angular speed is 2 pi radians in time of 1 period. What is its linear speed? Its linear speed is circumference, so 2 pi r divided by t. So you see this part, 2 pi over t, is exactly the same. Okay? So how can we write this? The link between these two is that linear speed is angular speed times radius of the circle. Okay, and this is first equation, which is very, very useful in the case of rotation. Okay, so if you are interested in this topic, please copy this to your notebook. Okay, so second, what is torque? To talk about torque, we have to review what the center of mass is. Center of mass occurred in your material. We're talking about center of mass in the topic about binary star system. Yes, I know your favorite topic. Yes. Okay, so we are talking about center of mass of 2 point masses m1 and m2 at distance d between. So what is a center of mass? Center of mass is a point where mass multiplied by distance between this mass and this point must be equal to other mass multiplied by the distance between this point and other mass. So basically, center of mass, so distance r1 from mass m1 is for r1 times m1 is equal to m2 times r2. Okay, so of course we know that r1 plus r2 is equal to d, so we can express this center of mass by, let's say, d and r1. So we can substitute r2 equals to d minus r1, obtaining equation that r1m1 is equal dm2 minus r1m2. We are looking for r1, so we can write r1m1 plus r1m2 is equal to dm2. Finally, r1 is equal r1 times m1 plus m2 is equal to dm2, finally obtaining equation that r1 is equal to m2 divided by m1 plus m2 times d. Okay, so the center of mass of the system of two-point masses depends on the masses, just on the masses or distribution of mass. Okay, what if you have a lot of points? Let's imagine that you want to calculate center of mass of three masses, m1, m2, and m3. Okay, there is a method you can calculate. First, you can calculate center of mass between m1 and m2, obtaining point somewhere, let's say here, depending on the mass. So you can imagine that this point focuses a mass of m1 plus m2, and then you can calculate center of mass between this point, which is center of mass of m1 and m2, and m3, obtaining a point which will be a center of mass of the system of three masses. And of course, in the system of more masses, you can do the same. Is it clear? Okay, of course, if you have objects which are real objects, not point masses, but real objects of real shape, you can use integrals, mathematical tool, to calculate center of mass. But for simple figures like a square or a triangle, centers of mass are known. In the case of square, is the center of square. In the case of let's say a rectangle, it's the center of rectangle. In the case of circle, is the center of circle. Moreover, in the case of simple three-dimensional shapes, are also known. Easy. If you have a cube, yes, you can plot diagonals of the cube, and center of mass will be at the center of the cube. The same sphere, center of mass of uniform sphere. Of course, I'm talking about uniform density all the time. So in the case of uniform sphere, center of mass is at the center of sphere. Okay. So let's write next point, a torque. Okay, this is something new. Okay, the symbol of torque in IB is this letter. Okay, and what is a torque? Torque is strongly related with rotation, not with a translation or typical displacement along the line, but with rotation. Is it clear? So this is something like a force, but in a rotation. This is equivalent of force in the rotation, not in the translation. So what is needed to translate something? Of course, a force. What is needed to rotate something? A torque. Okay, so let's imagine that you have a point of rotation, a pivot. Okay, and at given distance, let's imagine that this rod has no mass, yes, and force is applied to this rod at given distance r. And let's imagine in the first example that force, the directional force, makes a right angle to the direction which connects this point with the pivot. So what is a torque in this case? In this example, torque is given by product of force and this distance. Okay, Let's imagine that you have the same situation, but now force makes an angle which is not 90 degrees. Let's name this angle of alpha. Okay, in the case of this situation, you have to, if you want to rotate this rod along this point, the center of rotation or pivot, you have to take only part of the force which acts perpendicularly to the line which connects this point when force acts with the pivot. So what is the value or the length of this arrow? Of course, the angle alpha is also here, and this arrow can be written as F hypotenuse times sine of the angle. So finally you can define torque as a product of force times displacement times sine of the angle between direction of force and direction of displacement. Okay? So torque is very, very important in the case of rotation. I said this at the beginning. Okay, so let's now let's do first simple example. Let's imagine that you have a rod which has no mass, okay, which is able to rotate along this pivot. Yeah, and let's imagine that two forces act on this rod. Force 1 at the distance of r1 and force 2 acting in completely opposite direction at the distance of r2. Let's imagine that angles between directions of force and this rod are right angles. So angle here is 90 degrees and angle here is 90 degrees. Okay, and let's imagine that we have some data. R1 is, let's say, 80 centimeters and F1 is, let's say, 40 of newtons, and R2 is, let's say, here let's take 40 centimeters, and the value of F2 is equal to 30 newtons. And the question is about overall or net torque acting on this system. Okay, so let's focus first on force F1. I'm going to use a blue color for F1 and R1. Force F1 makes a torque which acts in clockwise direction. I'm going to use a symbol like this to show this clockwise direction, and is equal to F1 times R1. We don't need to write sine because the angle is 90 degrees, sine of 90 is 1, so it will be 40 times R1 is 80 centimeters, so 0.8 of meters. Okay, so it's 32 newtons. Let's focus on F2, which is at distance of R2. Okay, this force makes an effect in completely opposite direction. Due to this force, system wants to rotate counterclockwise. So the torque has a direction of counterclockwise, which is equal to value of F2 times R2. The angle is equal to 90 degrees. Sine of 90 is equal, of course, 1. I can omit this trigonometrical function, obtaining F2, which is equal to 30, times R2, which is equal to 0.4, obtaining value of 3 times 4, 12 of newtons. So what is an overall torque? Overall torque is a difference between torque which acts clockwise and torque which acts counterclockwise, because effect is in completely opposite direction. I've made one mistake. Torque is measured in Newton meters, not in the newtons. Sorry, here I wrote newtons, it's of course Newton meter. The difference, 32 minus 12, is 20 Newton meters, and effect is in clockwise direction. Okay, it's not difficult example, so I hope you understand this. Okay, let's take another example, a little bit more complicated. Yeah, let's imagine that there is a kind of a bridge. Okay, a bridge which has a wooden part like a rectangle, okay, which has a length of, let's imagine here, L of 5 meters, okay, which is hanged by a chain here, which makes angle of 60 degrees to the vertical wall. Is that clear? Okay, the pivot, the point of rotation, is here. And let's imagine that mass of this bridge is 2000 of kilograms and length of 5 meters. And the question is, the bridge is in equilibrium. What does it mean? Equilibrium now equilibrium means something different, because in the case of movement we have translational equilibrium, which means that the bridge doesn't move, doesn't accelerate left, right, up, down, okay, and rotational equilibrium, which means rotation, which means that the bridge doesn't rotate around this pivot. It doesn't move, it doesn't accelerate, it doesn't experience any torque in the clockwise or counterclockwise direction. Okay? Which means that all torques acting in clockwise direction must be balanced by all torques acting in counterclockwise direction. Okay, so what makes a torque in clockwise direction? Torque in clockwise direction is made up by gravitational force acting on this part. Of course, gravitational force acts in the center of mass of this rod. If rod is uniform, we can say that this r distance between pivot and center of mass is at the middle of length of the rod. And what is the angle? The angle between the gravitational force and this rod is 90 degrees. Of course, assumption is that this bridge is horizontal. Okay? And so how can we write it? It will be Fg times R1, which is mass times G times R1, which can be calculated. Mass is given, G is given. I'm going to use 10, of course. If you want to be more precise, then use 9.81. And distance R is half of L, so 2.5 of meters. So we have 20,000 times 2.5, 50,000 of Newton meters. 25 times 2 is 50, and 3 zeros 50,000. Okay, what is a counterclockwise moment? Counterclockwise moment is made only by tension of this string. I'm going to use Ft, or of this chain, which acts at distance of L from the pivot. Okay, so remember that this force makes angle which is not 90 degrees. Of course, in this case it's easy. 90 degrees is here, this angle is 60, so alpha is equal to 30 degrees. So it is tension, which acts at distance of L, this distance is L, length of the rod, and sine of 30 degrees, which is tension, which is unknown, L is 5, and sine of 30 is half, which is 2.5 of Ft. So finally, we know that total torque must be equal to 0, which means that clockwise torque must be balanced by counterclockwise torque. So final equation is that 50,000 is equal to 2.5 of Ft. So Ft is 50,000 divided by 2.5, which gives 20,000 of newtons. So what is the answer? Tension of this chain is 20,000 of newtons. So we've used simple model of simple torque to find the tension of this string. Okay? Let's do last example, the most complicated today. Let's imagine again that you have a uniform rod of given length. Let's imagine that the length of this is 10 meters. Okay, and mass of this is 1000 of kilograms. Let's use G equals to 10 meters per second squared. And let's imagine that this rod is suspended by two supports. Okay, S1, which is at distance of R1, which is 1 meter, and support 2, which is at distance of R2, and let's take R2 as 2 meters. R2 is measured from the right end of this rod. Okay, and question is, what is a force created by support 1, so F S1, and by support 2? Again, the force is not uniformly distributed because support 1 is at different distance from the left end of the rod than support 2 from the right end of the rod. Okay, so to solve this, we have to use two equations because we have two unknowns. So let's start with first equation for translational equilibrium. We know that this rod doesn't move down, doesn't move up, doesn't accelerate, which means that the gravitational force which acts at the center of the rod must be equal or balanced by support 1 and support 2. There is only one force acting down on the object, Fg, and two forces acting up on the object, Fs1 and Fs2. So this is our first equation. We can use data. Mass times gravitational acceleration is equal to Fs1 plus Fs2. So 1000 times g, which is 10, so 10,000, is equal Fs1 plus Fs2. This is our first equation. Okay, and second, we can use rotation. Also, we can balance a torque. In this case, we know that object, this rod, doesn't rotate, so you can take a pivot at any point you want. I think that the best is take the beginning of the rod as a center of rotation, because again, all momenta must be balanced. So let's look. Moment which acts due to the pivot in the clockwise direction is made by gravitational force. Okay, so moment in the clockwise is gravitational force which makes 90 degrees with the rod and is at the distance of half of L, because the center of mass of uniform rod is at half of its length. So it is mg half of L, which gives m is 1000, g is 10, half of L is 5, so we have 10,000 times 5, 50,000 of Newton meters. Okay, so 50,000 of Newton meters is a moment created by gravitational force which tries to rotate this rod clockwise, of course around the pivot which is located at the beginning. Okay, so what is a moment which acts counterclockwise? Moment which acts counterclockwise is created by these two supports. First support is at distance of r1, so it can be written by Fs1 times r1, and second support is at the distance of length of the rod minus r2, because distance from the pivot to Fs2 is L minus r2, so it will be Fs2 times L minus r2. Okay, so we can write Fs1 is unknown, is at distance of r1, so 1, plus Fs2, which is unknown, which is at distance L, which is 10, minus R2, which is 2, so at distance of 8. So we have equation, our second okay, not yet. And we know that object doesn't rotate, which means that moment which acts clockwise must be balanced by moment which acts counterclockwise. So we can obtain, we've obtained equation that 50,000 is equal to fs1 plus fs2 times 8, and this is our second equation. Now simultaneous equations, this and this, okay, give us a solution. By using first equation, we can write that fs1 is equal to 10,000 minus fs2, substitute to second, so we have 50,000 is equal to 10,000 minus fs2 plus fs2 times 8, so 40,000 is equal to minus fs2 plus 8 fs2 gives 7 fs2. Finally, fs2 is 40,000 divided by 7. My powerful calculator, around 5,700 newtons. So if fs2 experiences a force of 5,700 newtons, then fs1 of course experiences a force of difference between 10,000 and 5,700, which is 4,300 of newtons. Okay, I hope that this lesson is very useful, especially for people who wants to study physics in the future, who wants to learn physics more. So thank you for watching. Any comments, suggestions below the movie on YouTube channel or via e-register. Okay, so thank you for watching. My next lesson will be about moment of inertia. So please, as your homework, read in your Tsokos, here in this Tsokos, next chapter, moment of inertia. We'll be doing moment of inertia next lesson, so tomorrow. So thank you for watching. Good luck and stay at home. Bye.